Athletes, here it is, a video about problems involving motion and integration. Well, let's just take a quick sec because maybe you're thinking to yourself, hey, I remember doing some questions involving motion earlier in the class. And so way back when we were learning derivatives, what we found is that if we had the position function s at t, that the derivative of s at t gave us our velocity. And then what we found out was the velocity derivative gave us acceleration. So you can probably already imagine what we're going to do here. We're now going to reverse the process. So acceleration, the antiderivative is going to give us that velocity, and the antiderivative of velocity is going to give us that position function. And now what I really want you to think about is, I think we know something important about acceleration due to gravity, don't we? And I think there's a constant there. And so this is you're gonna start to see the links between physics and calculus come together really quickly here again. Okay, let's check out a couple of these. Okay, so our goal is to determine the velocity and displacement given the derivatives. So here we go. A train travels on a straight track with a velocity of 40t minus 6t squared, where t is time in hours. How far has the train traveled in 2 hours? Okay, well, if we know our velocity is this, and we want to know how far I've traveled in 2 hours, and it's on straight tracks, but like look at that velocity function. So what we're going to do here is then we want to find our position function. So our position function will be the antiderivative of this. So let's take the antiderivative. So add 1, divide by it. Add 1, divide by it. Okay, and then don't forget our plus c, that constant here. Really, this is a differential equation, right? And so we've got 20t squared minus 2t cubed plus c. Okay, but what's this plus c? Well, we're assuming that we're going to leave, the station when time is 0, that our speed is 0, because we're not moving anywhere. Okay, so what's our initial value then? What's c? So we sub in our values, our initial conditions, just like that. And what we see right off the bat is c is 0. So what do we have? Well, we have then our position function is simply 20t squared minus 2t cubed. Okay, so the question is, well, how far did the train move in 2 hours? Well, what we want to know then is s at 2. So we sub in when time is 2. And solving for this, we're going to end up with 64 kilometers. And there it is, friends. There's how far we've moved in 2 hours. All right. So, I mean, that's, a simple one where they've given us the velocity function. Not too exciting. What's more important is when we get a question like this. An object is being thrown, in this case a penny, off a building that's 80 meters high with an initial velocity of 3 meters per second. How long does it take for the penny to hit the ground? Well, I mean, let's envision this thing. So the penny is being launched here, 80 meters off the ground, and woo, comes down, bam, hits down here somewhere. And that's what we want to know. How long does it take for the penny to hit the ground? So that's what we're looking for right there, that value. Okay, so how are we going to start this then? Well, what I'm going to say is like, oh, geez, there's not a lot of given information, or at least it doesn't feel like there's a lot of given information. But I do know something important. I know acceleration due to gravity is negative 9.81 meters per second squared, right? So that's a fact I want to know. So then what do I know then about velocity? Well, velocity is the antiderivative of this. So velocity is going to tell me negative 9.81 t, right? So we're going to take the antiderivative with respect to time, plus c. So there's our differential equation. Okay, let's solve for c. Well, we've got this initial condition of when the velocity is 3 meters per second. Well, that's when time is 0. So we're going to sub that in that initial condition. So 3 is equal to negative 9.81 when time is 0. So we can see right off the bat that c is 3. Okay, what do we have now? Well, now we've got our velocity function with respect to time is this. Now, we're getting there. We want that position function so that we can tell how long it takes to hit the ground. So to find the position function, we're going to take the antiderivative of the velocity function. So negative 9.81 t squared divided by 2 plus 3t plus c. And again, there's our differential equation. Again, we've got another initial condition. This thing was launched from a height of 80 meters when time was 0. And so we let t be 0. And guess what? Our next initial condition is when c is 80. So now we have our position function. Our new position function, I'm just going to run it over here. Our new, or our only position function, I should say, is going to be, well, negative 9.81 divided by 2 is negative 4.905 t squared plus 3t plus 80. Okay, so now if I want to know when this penny, I was almost said rock, but penny, same idea, hits the ground, well, what we've got to do is solve for this. So from here, friends, all we're going to do to solve for this thing is we're going to use the quadratic equation, the quadratic formula, and we're going to find that positive x-intercept, or I should say positive t-intercept in this case, as we're dealing with t. And so all, again, you're going to do here is you're going to say, okay, t is equal to, and we're just going to sub in your values, plus or minus b squared minus 4ac over 2a. And I'll leave that up to you to do. You've been doing the quadratic formula since a long, long time, grade 11, and you should end up with a value of approximately 4 seconds to hit the ground. Okay, friends, so the really important part of this video that you need to know is really you're working with differential equations and you're trying to find that c value using your initial conditions. And I really need you to know this, that acceleration due to gravity is negative 9.81 meters per second squared. Okay, friends, there it is, a short one to end.